We will now introduce Pascal's principle. Pascal's principle states that a change in pressure within a static fluid will be transferred undiminished to every point within the fluid. In order to derive the resulting relationship, we will explore the operation of a hydraulic jack. This diagram represents the key components of a hydraulic jack. Notice first of all that we have a container, and the container is filled with fluid represented in blue. On one end we have a piston that's free to move up and down, and the cross-sectional area of this piston is noted as A1. On the other side we have a much larger piston, and its area is represented by A2, and notice that the large piston is supporting a car. Now this car is exerting a downward force on this piston, and of course this downward force would equal the weight of the car. On the left-hand side we have a force of F1 being applied to the smaller piston, and as a result the system is in static equilibrium. We're going to prove that we can actually maintain the static equilibrium. In other words, we can lift this car with a small force on the left-hand side as compared to the weight of the car. We will prove this by applying Pascal's principle. Now again, Pascal's principle states that a change in pressure within a static fluid will be transferred undiminished to every point within the fluid. That means that when the car applies this force against the piston, we're going to change the pressure in the fluid. We will represent this pressure as P within the fluid, and since this piston is pushing down against the fluid will react by pushing up against the piston with a pressure P. On the left-hand side, F1 also creates an increase in pressure. By pushing down on this piston, we're increasing the fluid pressure, and as a result, the fluid will react by exerting an upward pressure against this piston. According to Pascal, these pressures must be equal because a change in pressure within a static fluid must be transferred undiminished to every point within the fluid. In order for the fluid to maintain equilibrium, these two pressures must be equal, given the fact that we are at equal elevations within the fluid. As a result, we can write the following equations. On the left-hand side, the pressure just equals the force divided by the area. In this case, the pressure equals F1 over A1. On the right-hand side, the pressure equals F2 over A2. And again, according to Pascal, both of these pressures are equal. Therefore, we can equate the two right-hand sides and obtain F1 over A1 equals F2 over A2. This is the first form of Pascal's principle, If we multiply both sides by A1, we can obtain the second form. The second form looks like this. We can label the forms as form number 1 and form number 2. These forms represent Pascal's principle, and we can use the second form to prove that F1 is much smaller than F2. Notice that in our hydraulic jack, A1 is much smaller than A2. Let's assume that A1 has a value of 1 square meter and A2 has a value of 10 square meters. If we apply these values within this equation, F1 will equal 1 over 10 times F2. In other words, F1 will equal 1/10 of F2. What does that mean? That means if the car weighs, let's say, 1,000 pounds, we can maintain the static equilibrium. In other words, we can lift this car by simply exerting 1/10 of the weight of the car. In other words, 100 pounds. And so 100 pounds on the left can lift a 1,000 pound car on the right, assuming that the area on the left equals 1/10 of the area on the right. We will apply Pascal's principle within the following application. In this application, a student wishes to balance the car shown above by applying a force of 600 newtons on the left side cylinder. If the left side cylinder has an area of 12 square centimeters and the right side cylinder has an area of 95 square centimeters, determine the weight of the car, assuming the system is in static equilibrium. As you can see, the force that we're applying to the left-hand side equals 600 newtons, and we noted that force as F1. The area of the left side cylinder is given as 12 centimeters squared, and that needs to be converted. Of course, 100 centimeters equals 1 meter, and we will square that conversion factor. Therefore, the area equals 12 times 10 to the minus 4th square meters, and this is the left-hand area, which equals A1. The right side cylinder area was given as 95 square centimeters, and we need to convert that as well. Using the same method, and the result equals 95 times 10 to the minus 4th square meters. We need to determine the weight of the car that can be supported with a 600 Newton force applied to the left-hand side, and of course the weight of the car simply equals the force that that car exerts on the right-hand cylinder, which we labeled as F2. So we'll make a note that the weight of the car just equals F2 within our equation, and we need to find F2. We can find F2 by using the first form, or the second form for that matter. And so we have F1 over A1 equals F2 over A2. That results in 600 over 12 times 10 to the minus 4th equals F2 over 95 times 10 to the minus 4th. we can cross-multiply both sides, and the result will look like this. Notice that the 10 to the minus fourth can be canceled from both sides. Which produces an outcome of 12F2 equals 57,000. If we divide both sides by 12, F2 equals 4,750 newtons. And so, with a small force of 600 newtons, we can lift a car that weighs 4,750 newtons. We will now introduce the buoyant force and Archimedes' principle. The buoyant force is defined as the net upward force that is applied to a submerged object by the surrounding fluid. The symbol for the buoyant force is just B, and of course the units are newtons. We will derive the equation for the buoyant force by considering an object that is submerged within a fluid. In this diagram, we have a container, and the container is filled to the brim with a fluid. We're about to insert an object into this fluid, and as a result, fluid is going to overflow from the side of this container, and I've generated a plate underneath to capture the overflow of fluid. In this diagram, we note that the object has been submerged, and we also note that there are two forces acting on this object. The first force is the weight of the object, and the second force is the buoyant force. The buoyant force, again, is the net force exerted by the surrounding fluid upon the object, and it's always directed upward. The buoyant force takes into account the surface pressure, the pressure at a depth, and in essence it rolls all of those considerations into one force called the buoyant force, which we represent as B. Now notice that when we drop this object into the fluid, a lot of fluid has overflowed, and we captured this overflowing fluid in this pan. This is significant, and we will discuss this when we introduce Archimedes' principle. Archimedes' principle states that the buoyant force acting upon an object that is submerged within a fluid, will equal the weight of the displaced fluid. In other words, if we weighed this displaced fluid, the weight of this displaced fluid, which is of course the fluid in this pan, will equal the buoyant force. And so we can write that the buoyant force equals the weight of the displaced fluid. Which again is the weight of the fluid in the pan. So how much does this displaced fluid weigh? Well, let's remember that this displaced fluid occupied the same space as our object. Therefore, the volume of this displaced fluid equals the volume of our object. Now, this is only when the object is totally submerged. When the object is only partially submerged, then we would only consider the portion of the object that is below the level of the fluid. Let's determine the weight of the displaced fluid. We can determine this weight by first considering the fact that the density of the fluid equals the mass of the displaced fluid divided by the volume of the displaced fluid. From this equation, we can extract the mass. The mass equals the density of the fluid times the volume of the displaced fluid. Of course, the weight of the displaced fluid equals the mass times gravity. And so the weight simply equals the density of the fluid times the volume of the displaced fluid times g. And we obtain this result by simply rolling the mass equation into the weight equation below. We noted earlier that the buoyant force equals the weight of the displaced fluid. In our analysis, once again, if we know the weight of the water in this pan, that weight equals the buoyant force, and now we have an equation for this weight as well as the buoyant force. Therefore, the buoyant force equals the density of the fluid times the volume of the displaced fluid times g. Let's also note that the volume of the displaced fluid equals the volume of the submerged portion of the object. When the object is totally submerged, then the volume of the displaced fluid will equal the volume of the object. However, when the object is partially submerged, we need to only consider the portion of the object that's below the surface of the fluid. We will now introduce an application which demonstrates the principles of buoyant force as well as Archimedes' principle. In this application, a block of wood with a cross-sectional area of 15 square centimeters and a volume of 1,140 cubic centimeters floats in a container of water as shown below. If the block has a density of 525 kilograms per cubic meter, in part A, we need to determine the height of the block. Let's note that we have a block. It's submerged inside of a container of water, and it's only partially submerged, so there's a portion above the surface and there's a portion below the surface. The cross-sectional area is given as 15 square centimeters. The density of this wood is also given as 525 kilograms per cubic meter, and we need to determine the overall height, which is specified as h. In order to determine the height, we can rely on the volume equation. The volume of this shape is simply equal to the cross-sectional area times the height. Now we have a choice. We can either convert the area from square centimeters to square meters and then convert the volume from cubic centimeters to cubic meters, or we can introduce these values into our equation and keep track of how the centimeters squared and the centimeters cubed cancel. The second method will save us a little bit of time, so let's use it. The volume again is given as 1140, and I'll introduce the units just so we can keep track of the cancellation. The area was given as 15 square centimeters, and we're multiplying the area by h. If we divide both sides by the 15 square centimeters, we obtain 1140 cubic centimeters divided by 15 square centimeters. And a cubic centimeter divided by a square centimeter just produces a centimeter, because centimeters cubed over centimeters squared just equals centimeters to the first power. As a result, the height equals 76 centimeters, which could be expressed also as 0.76 meters. In part B, we would like to determine the block's mass. In order to determine the block's mass, we can use the density equation. We know that the density of the block equals the mass of the block divided by the volume of the block. And it's very important to distinguish between the density of the block and the density of the fluid, as well as the mass and the volume of the block and fluid. We have to keep clear regarding which mass, which volume, and which density is applicable. In this case, we're looking for the mass of the block, therefore we're tying that to the density of the block as well as the volume of the block. Let's solve this equation for mass, and if we do that, we obtain the mass of the block just equals the density of the block times the volume of the block. Now, the density was given in the proper units, kilograms per cubic meter. However, we can't multiply the density in these units with a cubic centimeter. Therefore, we have to convert the volume from cubic centimeters to cubic meters. So the volume was given as 1,140 centimeters cubed. We know that 100 centimeters equals 1 meter. However, we need to now cube the conversion factor. And by the way, 100 cubed is 1 million. And 1 million on the bottom can be expressed as 10 to the minus 6th power on top. Your calculator will produce that outcome as well. So the volume of the block equals 1,140 times 10 to the minus 6. On your calculator, you might be seeing 1.140 times 10 to the minus third. These two values are equivalent. And so the mass of the block simply equals the density. That was given as 525. The volume we just calculated as 1140 times 10 to the minus 6, and as a result, the mass of the block equals 0.5985 kilograms. In part C, we would like to determine the magnitude of the buoyant force. The buoyant force is represented by B, and in order to determine the value of B, we're going to use the buoyant force equation. The buoyant force equation states that the buoyant force equals the density of the fluid times the volume of the displaced fluid times G. Now the fluid is water, so we know that the density equals 1,000. Kilograms per cubic meter. We know the value for G, however, we don't know the volume of the displaced fluid. In other words, the portion of the block that is submerged represents the volume of the displaced fluid. However, we don't know how much of the block is submerged. We found the overall height from here to here equals 76 centimeters. However, we don't know which portion of this height is underwater. Therefore, we can't determine the buoyant force using the buoyant force equation. Fortunately, we have an alternative to this equation. The alternative is to construct a free body diagram and solve for the buoyant force using Newton's second law. So let's mark the fact that this equation is not working for us at this point, and we're going to use a free body diagram instead. As you recall, we constructed a free body diagram when we derived the buoyant force. Here's the diagram that shows us the free body diagram for a submerged object. The weight acts on the object, as does the buoyant force. Here's our block of wood, and of course the weight is acting on the block of wood. And the weight equals mass times gravitational acceleration. We found the mass earlier. The value for mass was 0.5985. G, of course, equals 9.8. And as a result, the weight equals 5.865. The buoyant force is also acting on this block. And the block is in static equilibrium. So according to Newton's second law, if we add the forces in the y direction, they will equal 0. Notice that we only have two forces acting on this block, and we can introduce them into our equation as B minus W equals 0. The weight, once again, equals 5.865. And if we transfer it to the other side, we can easily obtain the value for the buoyant force. So when the equation is unable to provide us with an outcome, Newton's second law is an alternative. In part D, we would like to determine the height of the submerged portion of the block, which we noted as B, small case b. Here it is. As you can see, the distance from the surface of the fluid to the bottom of the block is noted as B, and we need to find this dimension. Since we determined the value of the buoyant force, we can use the buoyant force equation to find the height B. So the buoyant force equation, once again, equals the density of the fluid, the volume of the displaced fluid, times G. B was calculated, the density of the fluid is known, and so is G. Therefore, we can use this equation to calculate the volume of the displaced fluid. And if this volume is somehow related to the height of the submerged portion of the block, then we can use it to find that height. Let's examine the relationship between the volume of the displaced fluid and the height of the submerged portion of the block. From this diagram, we can note that the volume of the submerged portion of this block equals the area of the block times the height of the submerged portion. Therefore, this volume equals the area, and the height of the submerged portion was noted as B within our diagram. So let's solve for the volume of the displaced fluid, and then we'll connect it to the height of the submerged portion and solve for that as well. The buoyant force was calculated as 5.865. The density of the fluid is 1,000. We're trying to determine the value of the volume for the displaced fluid. And G, of course, equals 9.8. If we solve for the volume of the displaced fluid, we obtain 5.985 times 10 to the minus fourth cubic meters. We already established that the volume of the displaced fluid just equals the area times the height of the submerged portion of the column. Before we apply this equation, the area has to be converted from square centimeters to square meters. The area was given as 15 square centimeters. Once again, we know that 100 centimeters equals 1 meter. We need to convert this by squaring the conversion factor, and as a result, the area equals 15 times 10 to the minus fourth square meters. Once again, the volume of the displaced fluid was given as 5.985 times 10 to the minus fourth. The area was just calculated as 15 times 10 to the minus fourth. And all that's left is the determination of B. The result for B equals 0.399 meters, which could be expressed as 39.9 centimeters. And so the overall height of the block was found to be 76 centimeters, and we just found that only 39.9 centimeters of the block is submerged. In part E, we would like to determine the distance between the top of the block and the surface of the water. So here's the top of the block and here's the surface of the water, and the distance between these two we noted as A. Let's also note that if we add A, which is the portion above the water, to B, which is the portion below the water, those two values will add up to the overall height of the block. So we can make an equation out of this because we know H and we just calculated B. As we noted, A plus B just equals H. We found the value of B equals 39.9 centimeters. H was calculated as 76 centimeters, and if we transfer the 39.9 to the other side, the value for A simply equals 36.1 centimeters. In part F, we need to determine how much additional force must be exerted on top of the block so that it becomes completely submerged. We're going to have to construct another free body diagram in order to determine the value for this force. This diagram shows that the block is now completely submerged because an additional force is applied to the top surface. Let's now construct a free body diagram that represents this situation. And so here's our block, and we need to account for all the forces that are acting on it. Well, of course, the weight of the block is pulling it downward, and the weight was calculated as 5.865 newtons. The buoyant force is acting on the block, but this is a different buoyant force. The buoyant force we calculated earlier only considered the submerged portion of the block. Now that the block is fully submerged, the buoyant force will be greater. So we have to recalculate the new buoyant force. There's also this additional force that we're seeking to determine. And that force is pushing the block downwards and forcing it to be completely submerged. The buoyant force equals the density of the fluid times the volume of the displaced fluid times G. We have the density of the fluid, and we also know the volume of the displaced fluid. In this case, the volume of the displaced fluid just equals the volume of the block, and that's because the block is completely submerged. The density of the fluid equals 1,000. That's the density of water. The volume of the displaced fluid equals the volume of the block, which was given in the body of the problem. That volume was given as 1,140 cubic centimeters, which we later converted to 1,140 times 10 to the minus 6, and let's insert a cubic meters into this solution. So we can roll this value into our buoyant force equation. Finally, we need to multiply this expression by 9.8. As a result, the buoyant force equals 11.17 newtons. We're now ready to apply Newton's second law. According to Newton's second law, if we add the forces in the y, those forces will add up to 0 because the block is in static equilibrium. There are 3 forces acting on this block. They are the buoyant force, the weight, and the additional force. Notice that the additional force is acting downward, and so is the weight, which is why we entered them as negative values. The buoyant force has a value of 11.17. The weight equals 5.865. The additional force is unknown, but not for long. If we transfer the additional force to the other side, we obtain 5.305 newtons. And so we will have to press down on the top of that block with an additional 5.305 newtons in order to force it to be completely submerged. There's one final note that I'd like to bring to your attention, and that's the relationship between atmospheres and pascals. Atmospheres is a unit of pressure, and it's abbreviated as ATM. Sometimes pressure is expressed in atmospheres, and whenever this occurs, that pressure has to be converted to pascals using the following conversion. One atmosphere simply equals 1.013 times 10 to the 5th pascals. And that concludes this lecture.